to do, and if you do everything, then it's great. If you do even one of them, it's still, in some cases and in some programs, extremely significant, especially the first two, the weight and the cost. So the structures consist of standard parts, and what I want to talk more about is going through some parts and talking about individual failure modes. If I have a standard skin, monolithic, which means that it's mostly a skin and it may have stringers or not, it might be stiffened or not, then there's always the material strength as a possibility. Basically, you exceed the strength of the material, whatever that constituent it is that might fail, fiber or failure. But that is usually not even of interest, because you have to design the so-called damage-tolerant design. You have to design with typical damage present, because it's unavoidable that this will happen. So they have what we call the open hole tension, open hole compression, and then compression after impact, shear after impact, or even, in some cases, even though it's not that much of a driver, tension after impact. So once you put this kind of damage, you get a significant drop in strength. We'll see typical numbers and results later on today. And those become now a driver. But as if this were not enough, then you have all the stability related or buckling problems, and you can have the skin buckling as a whole, or the skin between stiffeners buckling, or the stiffeners buckling, and so on. Skin stringer separation, a fairly famous problem since the 787 issues that had stiffeners separating from the skin near terminating stiffeners. The huge mismatch of stiffness between a stiffener and a skin causes all kinds of problems. We'll cover that in a separate lecture further on down the line. Delamination, which is a fairly classical failure mode. Out of plane stresses develop even if you only have in-plane loads in some composite laminates. And then associated with rivets and fasteners, you have bearing failure, bearing bypass failures, inter-rivet buckling, and so on. Now, this is just a short list of what happens on a monolithic skin. Now, on the other side, if it were a sandwich, so this is the sandwich with a core in the middle, you still have the material strength, but now the face sheet or the core can fail, or the adhesive connecting them, so you have separate types of material strength failures. You still have the same notch strength concerns and buckling, and then all of a sudden you have specific failure modes to sandwich, and this is just an exercise in the English vocabulary at this point: wrinkling, crimping, intracellular buckling, delamination. This one, all these we'll see towards the end of the course when we cover sandwich separately. Failure modes on the one hand, on the other now you have to manufacture, and you have to come up with the best approach for the low cost, but at the same time to minimize your probability of failing in any given failure mode. For example, how do you attach a stringer to a skin? you can co-cure them, which means you are relying on the resin between the skin and the stringer to take the loads, the out-of-plane loads, and this may or may not be the best design. You can bolt them, and this is actually the strongest, but not necessarily the lightest. And because, as I was saying earlier, of the assembly issues, the assembly cost being related to how many fasteners or bolts you have to put through the structure, that could be driving your cost up. And then secondarily bonded, which means, okay, I'm not trusting my resin. It's not as strong as a regular adhesive, so I'm going to put some adhesive in between. The stringer and the skin. The frames attaching to skins and stringers, the same kind of story. Then cutouts. If you have a window cutout or any form of a cutout, as you manufacture, you have to decide, do I want to make it without the cutout and then cut the cutout where I want it, or do I want to mold the cutout in, which means the mold itself will have special provisions such that I only place my material around the location where the cutout will be. You can do either, and both of them have advantages and disadvantages. And every time you have a cutout, if it's structure like a fuselage, or even not as much a wing, but the fuselage definitely, like the window cutouts and of course the door cutouts, you need to reinforce. And designing the reinforcement itself becomes an interesting problem, and the reinforcement itself will have a bunch of requirements related to manufacturing. And we will talk about designing reinforcements at the end of this lecture, if all goes well. Okay, stringers, stiffeners, or panel breakers, anything that's longitudinal, carries load along its main axis. And there's a bunch of different shapes that we are more or less all familiar with. I'm not going to go through them in detail. You'll see them later on throughout the course, some of them anyway. One aspect that I want to talk about now, and we will cover it in detail later, but I want it to appear as something you have at least seen once when we get to it in a few lectures, is that if I have a skin without any stiffeners, or if the stiffeners are extremely small, so they don't add much stiffness, then under, let's say, compression, if I look at a section cut here, I will get the skin to buckle in a large, typically single half wave along the length and along the width. If I add stiffeners, and those stiffeners, which are meant to be those vertical lines shown here, and those stiffeners are stiff enough, they actually will stay straight when the skin buckles, and the skin will only buckle in between the stiffeners. And those little circles, gray and white circles, are meant to be positive and negative half waves coming towards us or going away from us. And in this case, the buckling load increases tremendously. So you can improve the performance by simply using the stiffeners as what's called panel breakers. They break the panel. They do carry some load. You don't need to make them stiff enough to carry a lot of load, but you can make them barely stiff enough to keep the skin from buckling in between the stiffeners. So that's just what it might look like in reality. You've seen those at the hangar anyway, I'm pretty sure. In more detail, for one-dimensional structure used in aerospace, you have the material failure, which breaks the structure. You have the column buckling, where you have basically the entire stiffener buckles in as a column shown here. You have a very localized local buckling, which is called crippling. We'll cover that in special lectures because it's a bit of a nightmare and extremely important. It occurs quite often. But then you can have an intermediate half wavelength buckling. So this is very short wavelength. And then if your fasteners are separated far enough and your flange is not stiff enough, then it will buckle just between them. And that's inter-rivet buckling, and I wonder why we can't get the rest of this, but okay. And then skin stiffener separation. Imagine the skin here between these two stiffeners. When it buckles, this part is meant to come towards us, and this portion is meant to indicate that it's going away. It's the half wave moving away. That means the skin itself tends to pull itself away from the stiffener. So you develop out-of-plane loads. We'll see those later on in the course. The frames are very similar in that as long as you isolate the longitudinal one-dimensional members, which are called caps, basically you have the outer flange, if you will, which is also called the outer cap, and the inner one, which are essentially these one-dimensional stringers or beams, whatever you want to call them, and they fall under what we just discussed in the previous slide in terms of types of failure modes. And you then recognize the webs constitute simple plates, and those can buckle or can fail in strength and so on. And of course, if you then have cutouts, you have to decide how you design the structure around the cutout. This is meant to be some kind of reinforcement here to give you both the buckling resistance that you might need and the strength, especially when it comes to local failure around the hole because of the stress concentration effect of the hole. Decks and floors are just glorified skins which can have different designs. Remember the stiffened design, the sandwich design, the grid stiffened design. And you can have both in-plane loads and out-of-plane loads. Walking loads being one of the significant ones, and seat loads being another ones in the floor. And of course, impact loads, drop tools during maintenance, and so on. We'll cover impact on the second part of the course in a very, very much detail. Fittings. Fittings are these small gizmos that connect different parts. Therefore, almost by definition or as a rule, in many cases, they will carry load in 3 directions. As soon as you have load in a structure that's in more than 2 directions, that means there will be some part of the structure that sees out-of-plane loads. For a composite structure, that's a very important challenge, if not a problem, because the out-of-plane strength of the matrix used is so small that it makes it very difficult to design the structure without making it very heavy. Or if you decide, for example, to use fasteners or stitching to hold everything together, you make it very expensive. And usually there are these lugs. Basically, the fitting is meant to be this metal structure you can see here. And somehow, because of the requirement to connect, one of the best ways and most common ways is using lugs. A lug is basically this type of 2-dimensional structure. Even a simple lug, and I think we'll see it later on, and I will pass one around, will have more than one failure modes. Even if you're loading only in one direction, longitudinal in this case, you can fail on either side of the load next to the hole, which is the net tension failure, or you can fail by shearing or shear strength being exceeded along these two lines. That's a shear out. Or you can fail by elongating the hole and failing ahead of the hole in bearing. And these failure modes compete with each other. In fact, one can lead to the other. Doors and covers, not much other than basically what I wanted to mention here more than anything else is the minimum gauge. As your structure, if your structure is very lightly loaded, then you can get away with such low thickness that you run into other problems. In composites in particular, because of the moisture absorption concerns, if you make your structure very thin on the order of 2 to 3 plies, each ply being on the order of 0.15 millimeters, then over time, especially in a humid environment like the island of Guam, you will actually absorb a lot of moisture. This moisture goes through much more easily and can cause all kinds of problems, not only by reducing the local stiffness because the structure swells, but also because if you then freeze that water, that moisture, it expands and it can cause all kinds of additional problems. Well-known stories on the 737 horizontal stabilizers, which had been flying for decades. At some point, they took some of them off the aircraft and they sectioned them, and they found kilograms worth of water that had accumulated over the years, which had completely destroyed the core because that was a sandwich structure. But because it was